Experience has shown that data can be best described by relationships between entities. An entity is anything of interest about which data is recorded, such as roads, weather stations, etc. In general, there will be many relationships or associations linking the entities. Data modeling, that is, the production of a data model, is a formal representation of what data the product needs, expressed in terms that are independent of how it may be realized in software. Entity relationship data modeling is a particular kind of modeling that expresses data requirements in terms of entity types, attributes of entity types, and relationships between entity types. It is a widely used modeling technique which is effective for displaying the important elements of a data model for human understanding and communication. However, it is only one of a number of modeling techniques available. Many different kinds of relationship between entities have been identified, and there are many different ways of representing those relationships. Diagrams are often used to show relationships, but there are other techniques. The figure shown is one possible data model that describes a certain set of requirements. An entity may be defined as a thing which is recognized as being capable of an independent existence and which can be uniquely identified. It represents a thing that has meaning in a given context and about which there is a need to record data. For example, we can simply record the student entity type that defines the properties common to the collection of all students. Thus, student is the name of an entity type with properties of student identifier named student ID, student name, whether registered or not, and location, that is, region. An attribute is a component of an entity type that represents a single property of the entities of that type. Thus, student ID, name, registered, and region are the attributes of the student entity type. Note that the term attribute is a type concept, but it has become conventional to use the term attribute rather than attribute type. An important TRD modeling characteristic is that there is a specific way to distinguish entities of the same type from one another by using the idea of an identifier. An identifier is a particular attribute with the property of uniqueness, such that no two entities of the same type have the same value for that attribute. For example, the attribute student ID is the identifier for the student entity type. There are 3 roles for an identifier, and they are as follows: as an assertion of existence, an occurrence of the student entity type with the value S02 for its identifier is an assertion that a student exists and is registered with that student identification number. As a reference, an identifier such as S02 refers uniquely to a specific student. Given this identifier, we can examine the above table to discover that the student with this identifier is named Thompson. As a constraint, no two students can have the same identification number. A relationship is an association between entities that has a meaning in a given context which needs to be recorded. The degree of relationship is not an observation of relationship occurrences as they exist at some time, but it reflects an important part of the meaning of the relationship which holds for all possible occurrences. Thus, the one-to-many relationship asserts that a particular occurrence may be associated with many occurrences and a particular occurrence may also be associated with no more than one occurrence via relationship. The degree of relationship is not always one-to-many. Two other degrees exist. One-to-one, in which precisely one occurrence of an entity type may be related to precisely one occurrence of another entity type. Many-to-many, in which many occurrences of one entity type may be related to many occurrences of another entity type, and vice versa. Typically, when an event occurs, it affects the state of an object. A state machine is a model of the behavior of a single object over time and helps you to understand how that object's state affects its reactions to events. The figure shows a state machine diagram, known as a state chart diagram, in the UML, relating to the occupancy of a room in a hotel. In this problem, a room has two states: unoccupied and occupied. An unoccupied room becomes occupied when a guest checks into the hotel and reverts to being unoccupied when the guest checks out. The states are represented by rectangles with rounded corners containing their names. Transitions from one state to another are represented by arrows identified by the events that give rise to them. The solid black circle shows the initial state and indicates the starting state, that is, it says that a newly created room starts in the unoccupied state. The events that fire the transitions have been given simple names: guest checks in and guest checks out. Sometimes, the same event can give rise to different transitions and actions, depending on the prevailing conditions. To illustrate this, consider what happens when a hotel becomes full. If we identify two simple states, full and not full, for a hotel object, what happens as guests check in and check out? At some point, the hotel will be unable to accept any more guests. This situation is shown in the figure in this slide. The hotel is not full, provided that there is at least one room that is unoccupied. Checking out is not a problem in this example. Both instances of the event, check out a guest, lead to the not full state. However, an occurrence of the event, check in a guest, can lead to either the not full state or the full state, depending on whether or not the hotel has at least one room unoccupied. Hence, the guard conditions are mutually exclusive: last room and not last room. The figure contains two instances of a special kind of transition, known as a self-transition, that originates in one state and returns to the same state. From the perspective of checking in and checking out, the state machine in this figure is incomplete because it does not deal with the empty state. If every guest in the hotel checks out, the hotel is empty. You may wish to attempt the following learning activities. Their possible solutions are provided at the top of the Player tab. Thank you.